So let's start. So welcome to this class, which is about complex networks. Can you hear me well in the back? Yes, fine, okay. And I will start by introducing myself. So I'm Rémi Casabé. I'm associate professor at Université de Lyon 1. I'm a researcher in the LIRIS lab, so a lab in computer science. And I'm part of a team called Data Mining and Machine Learning. I was originally trained a computer scientist, but actually now I consider myself more a network scientist, and I will explain you more about what I think is a network scientist today. And I'm also a member of ICSI, so for those who are in the complex system option, you already know it well, but it's the Institute of Complex Systems here in Lyon. So you have already seen, I think, the website, but if you haven't, well, I invite you to have a look at my webpage, in which you can find all the information about this class. In particular, I will share the slides, so you don't have to write down what is on the slides. I will also share some what I call cheat sheets, which are some short documents in which there are all the formula in it. So it's simple if you want to have a quick look at what is in the class, with some references also in it, and sometimes some notebooks with code. I just started to introduce myself, so you haven't missed a lot. One thing is that I don't have a way to contact you, because as I said in the beginning, there are students from different masters, so maybe I have to write emails to every one of them. It's not convenient. So if you can please send me an email to the address which is here, or if you go to my website, you will maybe find another address in Gmail. You can also send your email there. And you tell me your name, your email address, obviously, and the master you are in. So yeah, I let this. You can find my email elsewhere if needed. So please send me this email, because and if you know some students who want to follow the class but are not here today, also please say to them to send me this email, so that I can have a complete list of all students following the class. I don't plan to do live streaming if we continue to be able to attend at the university, but I will try to record my class. So if it's working, it should record now. Hopefully, I will see if the sound is correct, but if it works, I will share the videos with you at the end. And if it doesn't work today, I will change my way of recording. There is also a Discord channel if you want to. It's not mandatory, but if you want to, you can go there. And it's more convenient if you have questions that can be helpful for others, or if you want to just ask me questions in a less formal way, you can ask on Discord, and I will answer you there. If you have questions about the class or about technical elements, something like that. The link is also on my website. So also on the website, I explained how is it organized, because since you are students from different masters and you don't have exactly the same requirements, there are actually two flavors of the course. Either you are from one of these two and you have 24 lectures, 24 hours of lectures and 6 hours of practicals, or you are from computer science and you have only 32 hours of lectures. Well, actually, the lectures are both lecture and practical, because we will code during the lectures. But anyway, they are differentiated. You can attend any of them. So if you want to come to the others, you can come. But officially, you should follow this organization. about the evaluation, so there will be no written exam this year. I plan to do a project. So the project will be the most important, 60% of the mark. You can work in group of 2 or 3, and I will explain more about that later. But basically, the idea is that you will take a real network and try to apply on it what you have learned during the class to understand, to say something interesting about it. And there will be also scientific article presentation. So it will be probably during the first week of January, or during the first class of January. You will do some scientific article presentation. Maybe some of you will do it earlier, but we will see the details also a bit later. About the lectures, so most of them are with me, but you will also have 3 classes with Christophe Crespel, which will be more focused on some specific topic. So when you have class with me, you need to bring your computer, because we will do in the first half like this. I'm talking, I'm introducing some concepts, and then during the second half, you are experimenting, so trying to code something using libraries in Python. So if you're not familiar with Python, it's not a big deal. You will learn during the class. You will also have, for next class, please install this software. It's also on my website, but called Gephi. It's a tool to visualize network and to do some basic computations on it. So please try to install it. You need Java, but if it doesn't work, we can install it during the class. So as I said, no need to write down definition that I explained here. I share this kind of documents where you have all the formulas in it, and the class is more to ask questions, to discuss about topics. So do not hesitate to ask me questions if something is not clear. That's really the goal of the lectures. Okay, so are there some questions first about these technical details? No? Clear for you? Okay, so then we can really start the class and discuss already about what are complex networks. Nowadays we talk more about network science. So originally the class was called complex networks, but for me it's more network science. So what is it? Why is it interesting to study it now? So I will start very broadly by explaining what for me is science. So science in general is about understanding how the world works, so how things work. And initially, how scientists have studied how the world is working is by looking at objects and trying to understand them globally as a whole. So you take, I don't know, the human body, and you try to understand by observing how people get sick and these kind of things. You try to drop an object, and you try to guess how this object is falling or how it's moving, what it depends on, these kind of things. So you look at the world as at the macro level, and you try to understand it directly this way, object by object. And then there was the great success of 19th and 20th century, which was the Redictionist approach, in which the idea was to say that if we want to understand the world, we want to understand things, we need to understand what things are made of. Okay, so we take a human body and we want to understand how it works. So maybe we need to look what is inside, what are the organs, and then we go inside and we try to understand what are the organs made of. So maybe we see that there are cells in it, and then we manage to look inside the cells, see that there is DNA and stuff and other things. And by decomposing like that all the things in the world, we managed to understand a lot of things and make really great progress in science. So this was a great success, but at some point it reached some kind of limit, because in the end we managed now to understand most, for instance, of what is in a human body until a certain level, of course. But for instance, the typical example is the brain. So maybe in the brain we know all the cells that are in it. We know basically what are inside these cells, how it works, so how the connection between them works. Of course, not all the details, but a lot of it. And still, we understand very little about how how consciousness or the mind or intelligence emerge from this bunch of cells. And this means that to understand more than that, to understand really how this works, we need to understand how things interact. So this is the classic idea of complex systems. It's that the whole is more than the sum of the parts. So even if you know all the parts and what is inside and how each part behaves, you still don't understand the whole system. You need to understand the elements and how they are interacting. So there are basically two situations when you have a system with many elements. Either it's homogeneous and it has kind of a regular structure. So it's not really important what element is interacting with what other elements. And in this case, if the system is homogeneous, then you can probably model it with equations. It works well because you don't have to care about how exactly it is organized. But in the other cases, when you have either heterogeneous elements, so many elements of different types that interact with each other, or if you have the same elements, but with a complex organization, with things that are not interacting randomly, but in a specific structure, then it's really important to understand how this system is organized and how elements interact, to understand the system. And that's where network science is needed, because network science is actually used, so networks are used to represent this organization, this structure of the system. And that's really what we will use network for, is to understand from a system how things works inside. So complex system composed of multiple parts in interaction, and we model the interaction between the parts. That's what I said. So here you have some examples of networks. So basically, you have on the top left, you have a social network like Facebook, so online social platform or social network in terms of humans. You have on the top right some public transportation system, but you can also look at transportation by car or bicycle or something else. You have example of a food predatory network, for instance. So ecosystems, basically. In ecosystems, you have interaction between animals, plants, and things like that. And you understand that some maybe elements of this system, of this web of predation in this case, you understand from the network that some parts maybe are more essential than others. Like if you remove one from every level, maybe everything do not destroy, but if you completely remove one level here, then maybe your network is completely, you lose the ecosystem might collapse. Another example here is an economic network. So in economy, you have also individuals that interact with products that are also linked to company, banks, and so on and so forth. So you have all these elements. And again, to understand an economic crisis, you need to look at not only who is failing, but when someone is failing, the impact will be with who this bank, for instance, is connected to. It's not the same impact if this bank is connected to only one another, or if it's like central in the network. So the brain, I already told you. Maybe also if you look inside materials, the organization is important. Here you have some city patterns. So it's cities seen from above, and you can see that just looking at the pattern of the graph of the roads, you can guess if you're in a city in Europe, for instance, or in the US or something else. And an example that you are very familiar with now, the question of diffusion in a social network. So diffusion, it can be of information, but it can be a virus also, of course. And so we will have, for instance, one class on diffusion, and we will see that. So, for instance, you're probably now familiar with the concept of the R numbers, that if it's above 1, then the virus will spread, and if it's below 1, then the virus will stop to diffuse, or at least not faster, not very far in the network, in the population. But actually, we will see that this is true if you have a homogeneous population, and that if your network is not homogeneous, if you have, for instance, hubs in it, so important people that have interaction with many different kind of people, even if your R score is above 1, maybe it won't diffuse, and if it's below 1, it can still diffuse depending on the organization of the network. A last point, so those from the complex system option probably already know about that, I've noticed about that, but this year, Nobel Prize in Physics was awarded to people working on complex systems. So it was in the Nobel Prize, so one of them, so Giorgio Parisi, was for the discovery of the interplay of disorder and fluctuation in physical systems from atomic to planetary scales. So here you have this idea of multi-scale organization, where you want to understand how the micro level interacts with the macro level, which is typical in complex systems. But the other ones actually were awarded for the physical modeling of Earth's climate, quantifying variability and reliability, predicting global warming. And just wanted to say a few words about that actually, when you want to build a model of the Earth's climate, you cannot just use a very basic model of how heat diffuses in the atmosphere, or how the clouds reflect the light of the sun. You have to build something which is complex, because you have many elements. You cannot just simplify it to 2 or 3 equations. You have really something complicated with many elements. So here, I think the orange one correspond to human activity, and the green one corresponds to natural phenomena. So each of these systems must be modeled using classical models. So some of them can be in economy, some of them can be from social science, some of them are from physics, clearly. And so each of these bubbles here needs classical models. But you see also that to understand the whole story, you need to kind of understand how all these elements are connected together. And again, you see that it's not homogeneous, that maybe if you act on some point here, you will be really at the interface between nature and human activity. And if you act, so you see that there are some arrows with directions. So if you act on something, you might act on something, it will have some effect on something else. So again, when you want to model something complex, you need to understand how the different elements are interconnected. So I try to convince you why network science is something really interesting. So network science is done by different disciplines. That's why you are from different masters here. So there are mainly physicists, computer scientists, mathematicians, sociologists, maybe that are the core of network science. And then you have many people who are, I would say, applied network scientists. So people from different disciplines that use these tools of network science to solve their own problem on their own research. So to conclude, in my opinion, of course, it's only my opinion because that's my topic of research, but I think it's not too far from reality. I think complex networks analysis should be, or will become, or is already, I'm not really sure, one of the basic tools of the modern scientists, a little bit like statistics. So whatever field of research you are in, if you work with data, you need to know statistics. You need to know what is an average, a distribution. You have to know how to compute what is a p-value. You need to have these kind of notions to interpret your data. And if in your data you have interaction between elements, well, you need to know about network science to interpret how these things are interacting. Okay, is there any question or remarks on this very general introduction? Not yet, okay. So brief history. So we originally but the beginning of network science as the beginning of graph theory. So with the Euler problem of the bridge of Königsberg, where the question was, can one cross across the 7 bridge and never cross the same bridge twice? So you can model this as a graph, and then you can prove that no, in this case, you cannot. Okay, so this is like the mathematical start of the field. Then in social science, maybe you can, we partially the beginning with the social network sociomatrix of Jacob Moreno, where he introduced this way of creating a matrix of who is friend or interacting with whom in a group of people. And actually, he started to draw graphs like that. So these graphs were made by hand at the time. So that's why you see it's kind of difficult to understand how it's organized. But nowadays, we have algorithms to do that more efficiently for us. Also here, a few key publications. So just to tell you that it's a recent field, of course, because one of the founding paper was in 1998. You see the small worm phenomenon that we will say a few words on. And just here, just to show that they are in different fields, and you can see that many of them were very impactful papers. You see the second lines, like the second most cited paper in Nature in this year, in that year, or another most cited paper in Science, in PNAS, in Nature Genetics, in the World Wide Web Conference, which is a computer science conference. So all of these papers are considered like founding papers in the field of network science. They are from different fields, and yeah, we will see a little bit of them during the course. But just as you see, so you can see 1998, 1999, 2002, 2004, 2010, and they are quite recent, but the field is, I think, growing even faster now. So the first, I think I have it just after. So here are just some books and reviews, but there are also references in my cheat sheets if you want. But for instance, this one is free. Oh, sorry. This one in the middle is very well known. It was written by Barabazi, which is a famous researcher in the field, and you can access it for free online. So if you're interested, you have many similar contents from my class, but not, I mean, the first 2 or 3 classes, at least, the content is relatively similar in terms of basic notions. And after that, I go on many different topics. But the other ones also can be interesting. Here you have some reviews on specific topics. We can go back to that later. If you're interested in a more general way, here are also some popular science books. I think they are interesting to read. I haven't read all of them, but at least this one and this one. This one I have it in my house. So if you want it, you can ask. I can give it to you. So yeah, they are just talking about networks in general. So and are enjoyable to read. So there are some journals specific to complex networks and network science, as you see from the name. And there are also several conferences specifically on the topic. And as you can see, they are quite recent, like they were created in the 2010. So it's, as I said, a new field. And that's all for my, again, general introduction. Here you have the program that you have on my website. And as you see, I have differentiated between what should be attended by everyone or by, so I changed the names, I think, in the last version, but by complex systems here. Here it's complex system, and here is computer science. So yeah, you can check details. Oh, just also a short notice. If some of you are interested to do an internship, I still propose one which is funded on graph analysis for illegal activity tracking in Bitcoin transaction network. It's part of a research project. But the problem is that if some of you are interested, you need to contact me very quickly before the end of the week, because I have other students interested, and so I have to decide on someone very quickly. But if you're interested, you can send me an email and we can discuss. I will put it on the Discord, the link to the internship. Okay, so is there? So we will start now the beginning of the class in itself, in which I will introduce all the basic concepts in this class of graphs and networks. So it won't be maybe the most fascinating class, because in the first one I have to introduce what is a network, some definitions. So, but I will try to make it not too bad either. So no questions on this first part? No. Okay, so let's start by defining what is a network, what is a graph. So a network, a graph is composed of what we call nodes and edges, or node and link, or vertex and edges. So you see that there are these two ways of seeing things, network or graphs. In the beginning, maybe graph comes more from computer science and mathematics, and network more from social science and then maybe physics. But basically, for me, I use the two terms interchangeably. So there is no, for me, it's the same thing. You have an example here, and your vertex can represent anything you're interested in, and your edges can represent anything you're interested in. So when we have a network, we will define it as a set, we will define it as a set of vertices, V, and a set of edges. Okay, so basically here you have an example where the graph is composed of V and E. You have V, which is here the list of the nodes, and E, which correspond to the list of the edge. And so you can plot this information, this graph, as this graphical form here. No problem here. We often encode the graph as an edge list like this. It's equivalent to a sparse matrix if you're interested, if you know about that, or an adjacency list. So adjacency list means that you have a node here on this column, and then you have all the neighbors which are listed just after. So the structure that you have to use in terms of coding depends on the application you want to make. So, but actually, what we will use in the experiments of this class are some libraries which exist in many different languages. So Python, C, R, whatever. In this class, we will use Python. And in this kind of libraries, you can directly manipulate the graph with the notion of network science and say, I want to add a node, I want to add an edge, I want to add a click, I want to add whatever. So you can ask, make this modification in network terms, and we will work mostly with that. Of course, you can also represent your graph as a matrix, but we will go back to that a little later. Let's talk about the different types of networks. So the most basic one introduced here is the undirected graph and undirected network. With an example here with the internet. So the internet is not the World Wide Web. It's the internet is when you have computers and servers which are connected together by physical connections. And this is undirected because information can flow in both directions. Okay. Then you have obviously directed networks in which you can say that the arrow will represent, for instance, the direction in which the information can navigate. So here you have an example with a citation network in which you have each paper which is citing another paper. So it's clearly in one direction and not the other one. Then you can have weighted networks in which on edges you will have some attributes of how strong this edge is. The example is a social interaction network. So clearly, we know that when you observe an interaction between people, maybe, I don't know, you can have a phone call data set, and you check how many times two people are calling each other by month, I don't know. And some people call each other only once per month in average, although it's twice per week. So obviously the strength of the connection is not the same, and you can represent this as a weight. Another type of network are bipartite network, in which you have two types of nodes. So for instance, it can be, so it's very often used by many companies, for instance, right now for recommendation system, in which you will have, for instance, some customers, some people, and here you will have some products. So this product can be items for Amazon, it can be movies for Netflix, it can be whatever. And you can represent here, so who is watching what movie with this graph, and then your objective is to do link prediction. So link prediction is basically who is, what is the next link that might appear. So what people are going to watch next, or what they might be interested in watching or buying or whatever. So we will walk a little bit. We will discuss a little bit about that when we will do some link prediction in the class on machine learning. But yeah, this kind of network are also quite commonly used. Another example here is a gene disease network, in which you will have one kind of nodes are gene, the other are disease. And what is important is that there cannot be links in this kind of network. There cannot be link between people and people, or between product and product. You have only people to product, for instance. So one category of nodes to the other. Then we can talk about multiplex or multi-layer networks in cases where you have several networks which are connected in some way. So the same node, for instance, here there are transportation network, and you want to know how to go, for instance, how Google is proposing you to go from one point to another in Lyon. Well, in Lyon, not so much, but in other cities. Well, they know the tram system, they know the street network, they know the bus system, and they know the interconnection between them, and they search for the shortest path in this multiplex, multi-layer network. But we will go a little bit in more details on that on another class. And finally, you have temporal and evolving networks. So networks in which things are changing with time. So in this case, and the one I will discuss in this class is when the topology of the network itself is evolving. So you have nodes and edges which are added and removed with time. So basically, most of the networks that we actually study are evolving networks, but very often, because it's simpler, we look at one particular point in time, or one aggregation of everything that happened over a month or a year or whatever, and we study it as a static network. But it's also important in some cases to study the dynamic aspect. And again, we will have a class specifically on temporal networks. Yeah, we will have a short break at 9. I will try to go a bit further before. So we have to define some basic notion on the network. There is first the neighborhood of a node. So the neighbors of the node are just the nodes that this node is connected to. Okay. One very important notion, so please remember it, because sometimes you forget about this word, is the degree of the node. So the degree is the number of links, number of neighbors. Okay, so how many connections you have. Then we can talk about successors and predecessor, which is the same thing in a directed network. So the successors are the node you have connections to. And in the same way, we can talk about the out degree and the in degree. So out degree is the number of connections you have to other nodes, and in degree is the number of connections to you. The weight of the node is of an edge, sorry, is the strength of the connection. And sorry, well, yeah, it has how what is the strength of the connection, and the strength of a node is the same thing as the degree, but with weights. So basically, it's the sum of the weights of the adjacent edges. Just an illustration of that. So you have this this network which is undirected. So the degree here is 2, and here it's 3 number of connections. So that is the degree. Here you have the number corresponding to the in degree. So this node has 3 incoming edges, but this one has only 1, for instance. And here is the out degree. You see that this node has 2 outgoing edges, so it has an out degree of 2. Here is the strength. So what we call the strength of a node is the weighted degree. So in red, you have the strength of the edges, and so the weight. And in blue, you have the strength of the node. So for instance, this one has a strength of 12 because it has one edge of weight 6, 5, and 1. So it's 6 plus 6 is 12. And the same for all the others. So obviously the degree and the strengths are often correlated, but they can also be very different in some cases. So this is for the basic definitions of what is in a graph. And now we will discuss on how we can describe graphs. So the idea is that if you want to study a system, so you choose how to model it, what are the nodes, what are the edges, you collect information, and now you want to describe your graph. You want to say something about it. For instance, to compare with another one. So maybe you can compare what you observed with a null model, so something which is the same, a network with similar properties but random, and see what is different in your network. Or maybe you want to compare 2 graphs corresponding to 2 different systems. I don't know, you want to look at one ecosystem in a country, another ecosystem in another country, and you want to compare these ecosystems, or in network in different years. Maybe you want to compare what happens in 2005 and in 2006 in Bitcoin, for instance, or whatever. So you model your system with graphs, and you want to say something and to compare them. So obviously, the first thing that you can do is to compute the size. So the size is just the number of nodes. You can also compute the number of edges, and naturally also the maximum number of links. So if everyone is connected to everyone, then that is the maximal number of links. And it depends, of course, if your network is directed or undirected. So basically, if it's directed, then each node can be connected to all the other ones. And if it's undirected, well, you have to divide by 2 because A to B and B to A are the same thing. So just some examples of networks I took from papers. And you have the description with the number of nodes and the number of edges. So obviously it can be very different. You can go from a small network like the brain of C. elegans has only 280 neurons, I think it is, and 6,000 edges. And you can go to very large network like Facebook, and it was only in 2015 here with 1.4 billion nodes and 400 billion edges. So of course, it's a little bit more difficult to analyze this kind of network, but all of them can be interesting. Basically, I tend to say that it can be interesting to study a network if you have more than 10 nodes. If you have only 10 to 12 nodes, something like that, it's not really interesting. Well, okay, maybe you can plot your network, but you don't have to analyze it with network science tools in general, because it's too little. But if you because you can understand it by just looking at it, you can understand it. But when you start to have hundreds of nodes, then you cannot understand how it is organized just by looking at it. So you need to use some tools to analyze it. Another notion is the density. So first, we have the notion of the average degree. So the average degree obviously is how many connections each node has in average of the degree. And the density is the fraction of pair of nodes which are connected by an edge. So you count how many edges you have in the network. You compute how many edges you could have in the maximal cases when everyone is connected to everyone. And you just divide the first by the second, and you get your density. So the fraction of pair which are connected by an edge. What I say here is that typically in real networks, so this is a property of real network when we observe them, they have usually a small average degree. So it means an average degree which is very small compared to the number of nodes. Okay. Of course, it's not mandatory in a graph. You can generate random graph with very large degree. But if you think about when you take real networks representing real systems, usually your degree will be small, maybe in the scale of the logarithm of it should be n here. It's the number of nodes. So for instance, let's look at the density for some networks, so the same as before. You see that your density is very, very small, very often when the graph is large. A very small fraction of the edges, possible edges exist. And so if you look at your average degree and you compare it with your number of nodes, you see that, yeah, it's very small. So you have to be careful with this notion of density, because this means that when your graph becomes large, you know that your density will tend to decrease. So you should not compare the density between nodes, between network of different size in terms of number of nodes. It has also been observed that when a network is growing, when it increases in size, then the average degree tends to grow, and the density tends to decrease, because the growth of the degree, of the average degree, is not proportional to the number of nodes which are added to the network. And you can understand this quite intuitively if you think about a social network. So something like Twitter or Facebook or whatever, your favorite one. You see that when it opens, I don't know, to a new market, and you have many people from a new country, or maybe from a different age. So maybe in Facebook you had in the beginning many people of 20 years old, and then you got many people that were older, maybe above 50 years old. And when you have some growth like that in terms of a large number of people, well, of course, you will know only very few of them. So even if you add millions of people, maybe you know only one or two. So when you add a lot of people to the network, it might increase your own degree by 1 or 2, because maybe among all these people, you know some of them, but it's not proportional to the large number of people that can be added to the network. Here is just a plot from a paper about the density of networks, where you can see that the degree here, you have the relation between the degree and the number of nodes in a bunch of different networks. And yeah, you see this observation that the mean degree tends to be low compared even when the number of nodes increases. Basically, degrees stay relatively small. Just an illustration of this. So another important notion is the notion of the distribution of the degree in the network. So for those of you who are not that familiar with distributions, I just remind you that you have very often many things are distributed in nature. Many things are distributed according to a normal distribution. So basically, if you take the height of people, how people are tall, you will think that maybe you will measure that in average people measure, I don't know, 1 meter and 65 centimeters. And if you if you plot the distribution of people, you will see that most of them are concentrated around this value. Okay, most people will be between I don't know 1 meter and 40 and 2 meters, let's say. You will have nearly everyone in this So this is, for instance, what you can observe if you look at the wealth of people. So how rich are people? You have many people who have low income. Well, it's maybe not that low, so you will have a peak maybe around here. And then you have a few people that have a very large income, very large revenue. And this is characteristic of some systems in which you have so we will see later what we call the rich get richer mechanism, which is common in many different systems, in which some elements so wealth attracts wealth, and so this creates this kind of distributions. And what is interesting is that if you create a random network, so we will have a class on random network, but basically you take nodes and you distribute edge randomly between them. Then the degree distribution is like the first one, is a normal distribution centered on the average degree. But if you look at real networks of many different things, from social network to economic network to the brain and many other things, you have rather the second distribution. You have a high majority of small degree nodes and a few large degree nodes that we call hubs. And this is modeled by a power law. So we will have a class, well, we will have a part of the class on this notion in particular and how it emerges from some mechanism. But for now, just remember that when you want to understand a network, what you can do is to plot this distribution and check if it's normal or if it's more heterogeneous, so like a power law distribution. Then the notion of subgraphs, so quite simple, but here it's so a subgraph is when you, so for instance, this is a single graph in which you have several connected components. So connected components are a group of nodes which are all connected to each other. You can reach one from the other. So here you have 1, 2, 3, 4 connected components. A subgraph is just a set of nodes and edges taken from a network. And an induced subgraph is a little bit more strict. From an original network, you select some nodes in pink here. And if you take all the edges that connect, that appear between those nodes, it's called an induced subgraph. And on the right, it's not an induced subgraph because this, you have the nodes in pink, you have selected the node in pinks, but you have selected these 3 edges, but not this one. So if you have not selected this one, then the graph composed of the pink elements here is not an induced subgraph of this one. Because if you select the pink one, you should select all the edges between these pink nodes to get an induced subgraph. So we often do that to study a part of a network. So for instance, if you want to create what we call an ego network in a social network, so you take one person, you take all its neighbors, and then you study the induced subgraph of this person and its neighbors. So for instance, I take my profile, I take all my neighbors, I create this network, this induced network, and I will see that it's organized in probably in parts where there is one part of the network that are people from my job, another part which are people from my family, another part with people from my high school when I was in high school, and so on and so forth. So you will have this. You will clearly see that this network is organized in different parts, and this is done by using an induced network. So I think we can make a short break. I would say 5 minutes now, and yeah, in 5 minutes we can continue this. Sorry, I need this with the mask. Let's continue our description of networks. So the next property is the clustering coefficient. So clustering coefficient or triadic closure is how much how many triangles there are is related to the number of triangles in the network. Triangles are considered important because they are especially more common in real networks compared to with random networks. So it's characteristic of what we observe in reality. You can understand that by thinking about what's happening in social networks, where we say that friends of my friends are my friends. So basically, if you know people from a group, you are very likely to get integrated maybe to that group, and then you will be connected to the other people in that group. So when you have connection with people, we will create connection with their friends and create triangles like that. Yeah. So there are several ways to count that. I will maybe won't go into the details. You can check that if you're interested in my documents. But basically, what you can do is to count the number of triangles in the graph, and then you count the number of possible triangles, and you compare the two of them. So here I show 2 ways actually of computing this clustering coefficient for one node. So here it's a clustering coefficient of one node. One way is to count how many triangles you have. So it's on the right here. You see that in the neighbors of this node. So this node U has neighbors, and you count how many triangles. Here there are 2 triangles. And you have a formula to count how many triangles are possible in the maximum. Here it's 6 because there are 2 combinations among the four neighbors. So this means open triangles. So you have 6 open triangles and 2 closed triangles. So you have a clustering coefficient of 1/3. Another way to count that is to say that among the neighbors of U, there are 2 edges, so 2, 1, and 2, and the maximum number of edges between them is 6. So it's actually computing the same thing, but in 2 different interpretations. And again, we have a clustering coefficient of 1/3. So this is to describe one node, but here we are trying to describe the network. So to describe the network, you can either compute the average clustering coefficient. So you compute the clustering coefficient of every node, and then you compute the average. Or you can compute directly a global clustering coefficient, in which case you will count how many triangles you have in the graph, how many triangles you could have, knowing the degree of nodes. So it depends on the degree of nodes. And you compute your global clustering coefficient in that way. So be careful. I don't know if I wrote it somewhere else, maybe not. Well, yeah, be careful when interpreting the value of the average clustering coefficient, because the problem is that when you have nodes with a small degree, only 2 nodes, for instance, if you have a node that has only 2 connections, then its clustering coefficient is either 1 or 0. But if you take a node with a large degree, then probably its clustering coefficient will be 0.2 or 0.6. So since we know that in real network we have many nodes with a small degree, it means that your average clustering coefficient will be strongly impacted by these small degree nodes that have only value that can be only 0 or 1. So this can be a biased perspective, and maybe in many cases you're better off computing directly the global clustering coefficient. So here's some examples of the global clustering coefficient on some networks. So you have, so this comes from this paper. You have many networks here which are analyzed with their size, their average degree, and here they compare the clustering coefficient which is observed in the network with the clustering coefficients computed on a random version of the same network. So same network means they keep the number of nodes, they keep the number of edges, they randomize the position of edges, and they compute the clustering coefficient on that network. And what you see is that actually the real value, in most of the case, is much larger than the random one. So this is a property, as I said, of many networks in which it tends to create triangles in it for several possible reasons that we will introduce in the class. But one can be, for instance, a spatial organization. So people are connected because they live close from each other, for instance. It can be proximity in space, but it can be proximity in I don't know, affinities or political opinions or whatever. This will tend to people who are similar tend to connect together. There is also the notion of a network which is organized in groups, in communities, and people inside the same communities will tend to form triangles to be connected together. Well, there are several explanations, but the fact is that in real networks there is a high clustering coefficient. So another set of notions are based on the idea of looking at path and walk and distances in the graph. So a walk is basically a sequence of adjacent edges or nodes, but when you can repeat nodes, so you can visit, I don't know, like A, B, C, but or in this one, like 4, 3, 2, 4, 2, 1, 2. This is a walk. And a path is a walk in which each node is distinct. So in this case, you have the right to go only once on every node. Obviously, there is the length of the path is just the number of hops that you're doing. So for instance, 3, 4, 2 has a length of 2. So it's a number of edges, not the number of nodes that you encounter. The weighted path length is the sum of the weights that you encounter. The shortest path is, so between two nodes is a path of minimal path length. So this is often a notion we're interested in. So for instance, if you want to go from A to D, you can check what is the shortest path. So there is one path like this, A, C, E, D. There is one path like this, A, B, C, E, D. And there is one path like this, A, B, D. So obviously the shortest path in this case is ABD. It's a path of length 2. But there is also the notion of the weighted shortest path, and the weighted obviously is when you take into account the weights. And you can see that, for instance, in that case, I think that if you go through the shortest path in terms of hops, you have a weighted shortest path of 14. But if you go this way, you have a weighted shortest path of only 4, 7, and 9. So 9 by this path. So again, this is the kind of tools you can use that road recommendation. How is it called? When you use a tool like Google Maps to find the fastest trajectory to go from one point to another, it usually computes some shortest path, considering the weight that corresponds to the time you need to cross the road, so the speed limit, for instance, and also the number maybe of terms that you have to make, number of change. So both of them are important. So maybe you need to consider both those aspects when you want to recommend the road to follow. And the distance is the length of the shortest path. So when I say what is the distance between A and D, in that case, you will say, well, the answer, if I don't talk about weight, the distance is 2. Okay? Even though there are several ways to go from A to D, when I just talk about the distance, it's 2 here because it's the distance of the shortest path. So obviously, computing the shortest path is something that can be really costly when your network is large. So I won't discuss that here. I think maybe Christophe Crespel will talk about that a little bit later in his class. I'm not certain about it, but you will see. No, just to tell you that there are some algorithms, obviously, that have been proposed to compute all the shortest path between all the nodes in a single, how to say, all together, so that it's more efficient than computing each of them separately, because this notion of path, shortest path is useful in many computation. As we will introduce in the next class, for instance, if you want to find important nodes that are essential to the diffusion of information in the network, you need to search for nodes that have many shortest paths going through them. And for this, you need to compute all the shortest paths, and you have algorithm for that. So if you want to, for those of you who are interested, you can have a look at that slide. So when you know the notion of, when you have the notion of shortest path, you can define the diameter of a graph. So the diameter of a graph is a notion that can be used to understand if it has some elongated parts. So we call whiskers that go maybe like you have a center of your network, and then you have some parts where you have one node and then one other one and one other node, and you have no strong way to reach the center of the network from these nodes which are at the periphery. So in that case, you will have a long diameter. So the diameter is the maximum distance between any pair of nodes. So the longest of the shortest path. Okay, you compute all the shortest path, you keep the longest one, the one with the longest distance, and that is the diameter of your graph. And even more informative is average distance. So the notion of the average distance is tells you how everyone can reach everyone easily in your network. So this average path length is connected to what some of you already know maybe, which is the famous 6 degrees of separations, which is known as the Milgram experiment. So the other Milgram experiment. So maybe you know the other one with the electric shock. It's the same Milgram, but it's a different experiment. This one is on networks. And here, so Milgram was a sociologist experimenter in the 60s, and he has made this experiment to know if the social network of people were had these short connections or not. So at that time, we had no Facebook and no online social network to look at. So it was really an hypothesis that maybe between two random people in the US, in that case, is there a small number of hops that allows to go from one to the other? Yes.
Just in the previous slide.
Yes.
Do we divide by the total number of the previous?
Even previous one. Yes.
We divide by the total number of possible nodes in the of possible edges in the graph.
Yes, it's the sum of the distance divided by all the possible pairs of nodes, because you want to compute the distance between all the pairs of nodes.
Mm-hmm. But if we have, for instance, a graph without too much edges, can't we just divide, for example, by the number of the edges?
By the number of edges?
Yeah. Yes.
Well, that will be a kind of a normalization in some way, yes. But in the usual way, it's really come from, if you start from any node will take at random, and if you want to go to any other node, what is the number of hops that you want to make? Okay. So that is the originality. But well, there are hundreds of papers describing different variations. I'm sure that you can also divide by the number of edges, and it will tell you something else, but normalizing kind of by the density. So in this experiment, the idea was to check this notion that we are close from each other. So basically, the question is, I don't know, if I want to shake hands with the president of the US, do I know someone who knows someone who knows someone who knows someone who knows him? And basically, I just have to go through a few steps to reach that person. The experiment was to give consisted in giving a mail to people, a physical mail, because it was 60, and you give them to random person, and you ask them to send this mail to someone else that they don't know, but what they know is the name and some information like the city they live in, maybe what they do as a job, what is their age, something like that. They have a few information about them, and they need to send them to give the mail to someone that will give the mail to that person. So they know the city, but they don't know the exact address of something like that. And so the idea is to navigate the network by giving the mail to someone who you think might be closer from that destination than you. So maybe if you live in Kansas and you need to send the mail to someone living in New York, then maybe you know someone directly in New York, and obviously you will give the mail to them. Or maybe you know someone in I don't know, in Iowa, and then that they know someone from another place which is closer, and so on and so forth. You can use again space or your social, maybe if you know someone who is very popular and they know many people, you know, they know everyone, so maybe you give the mail to them and they will have a better way to know someone who directly is close to this person. Or yeah, if you know someone who is young and you know that the destination is young, you might give it to them, or whatever strategy you want to use. they send the mail to their most relevant contacts, and then so you wait that all the mails arrive, and you count how many hops they have to make. So you know they write in the letter. Maybe if you were when you were younger, maybe you have known those chains when you send the emails to someone and they add their name and they send to someone else and so on. Here they do the same thing, and we count how many hops were needed to reach the destination. And in average, what Milgram has found in that case is that in average there was a need of only 6 hops. So that's where the 6 degrees of separation comes from. But at that time, there were many criticism on that because some mails did not arrive. It was a kind of a small sample, and there was a number of limits. Actually, maybe if you know the other experiment of Milgram with the electric shock, there are also some limits. And nowadays, there are many discussions about are these results reliable, or do they tell you something different that people? Well, anyway, I mean, I won't go to the detail in the other experiment, but there are some criticism on is it true or not. And when I started my PhD, I remember a conference where it was again a debate with some people saying no, but this notion of 6 hops, 6 degrees of separation, it's really biased because in reality it's much more than that. Actually, half of the mails did not arrive, so probably it's not actually true. But then it was the beginning of so the first one that was studied was the first network that was studied was the MSN Messenger system. And then of course you have Facebook, you have the World Wide Web, and you can start to make measurements on real networks with a lot of people in it, and to check how it looks like. And this was, for instance, a paper that was made on analyzing Facebook, like 4 or 5 years ago, maybe I don't remember exactly, but it was already a very large network. And you plot this average degree of separation. And actually what you have this distribution. And what you see is that it's actually much lower than 6, but it's more like 3.5 or between 3.5 and 4. So obviously you can make criticism on that too, because you might say, yes, but on Facebook, what you observe is not really a friendship. It's more like you add people that maybe you don't really know. But yeah, of course, you have to define originally what is what you want to compute. So you want to compute how many hops you have, but with what kind of connection? Weak connection, strong connection. Well, here with Facebook connection, actually, it's more like 4. So this means that basically, in average, for if you take a random person in the world, you know someone who knows someone who knows someone who knows that person. So we are pretty close from each other, basically. But of course, you observe that there are also some people who are more far away. And I think in this study, they computed the diameter of the graph, so the longest of the shortest path, and it was something like 18. So there are some people, 2 people in the network that need 18 hops to go from one to the other. But you have all this problem, of course, of fake accounts or accounts with only 1 or 2 connections. So here it's computed only on the main connected component. So but 99.99% of all the nodes are connected to each other. They are in this main connected component. Okay, so we know basically that in real networks, we have this property that in many cases, you have a short average distance. And this was one of the first paper I presented in the famous paper of network science. It was about the small world property. And here we can define this small world property. So a network is said to be small world when it has an average distance which is short. So it means something like the average distance is about the logarithm of the number of nodes. So it grows very slowly with the number of nodes. Short average distance, and a clustering coefficient which is high. So it means that you have a lot of triangles. You have a clustering coefficient which is much higher than in a random network. Because actually this average distance, which is short, is something, we will see it in the random network class, is something which is that you can also find in random network. So in a random network, you have a small average distance, but you don't have a high clustering coefficient. And then you can easily create a network that have a large clustering coefficient by just putting triangles, by having some regular structure. But in this case, you will have a long average distance. And so what is important about many of the real networks that model real systems is that they have this small world property in which they have an average distance which is small and a high clustering coefficient. So this is, again, something that is commonly the first thing you check when you have a network. Does it have this small world phenomenon? Some real networks do not have it. For instance, if you look at a network of streets, so I don't know, roads that you can take with a car, for instance, in France or in Europe or whatever, you immediately understand that it does not have an average distance which is short, because to go from Lyon to Moscow, for instance, I need to change many times the direction. I cannot change only 6 times my direction to go there. And the clustering coefficient is not really high because you do not, well, it depends on how you count, but basically roads tend not to form grids. So another notion, I will go slowly on the fast on this one, is the core periphery structure. So we'll talk more about that when we talk about how the network are organized. But you can compute some value of the K core, which tells you if your node, if your network is organized in a core periphery structure or not. So basically, if you have you count, you remove edges. Well, I won't go into the details here, but just know that, just remember that you can, and your network can have a core periphery structure or not. So a dense core of connected nodes all connected together, and more areas with less connected that are connected only to the center. Well, okay, I don't know I don't go into details. Another things you can do to describe your network is to count triangles. So if your network is directed, you see that you have many different types of triangles which are possible according to the direction of the edges. When you take any 3 nodes at random and you check how what is the direction of the edges between them, you obtain these possibilities. And you can understand that some patterns are typical of some types of networks. So for instance, this one will correspond to a diffusion structure. So you have one node that sends information to 2 nodes that do not send information back to that person. Then you have typical transitive features in which if you have AB and BC, then you have AEC, and you have everyone which is connected to everyone and whatever. So the fact is that you can count these triangles and observe again how it compares with a random network. So you take again the same network with the same size, the same number of directed edges, you randomize these edges, and you compare. So here for each of the possible pattern, you count how many times you expect to get them in reality, and how many times you observe them in the random network. And you observe if something is different. So for instance, if you see very often the pattern of diffusion, you can say, okay, maybe in my network there is this pattern of diffusion which is more common. So just an idea of how we can describe a network. Same idea, but with more than 3 nodes, you can compute the frequent graphlets. So there are algorithms that will find the common graph in your graph. And you might say, so for instance, I don't know, in a citation, a network of citation of scientific articles, maybe you will find that this pattern is exceptionally common I don't know why, but if you find that one particular pattern is exceptionally common in your graph, so more common than it should be in a random graph, then it's interesting, and you can study why this pattern emerge. Okay, so just some ideas for describing a network when you get it. I think it's the last part of the class today is a few words about describing graph as matrices. So I know that for some of you, depending on the master you're coming from, you're not familiar with matrix formulation, and some others are very familiar with it. So I won't go into too much detail here, but there are more details in the papers, in the cheat sheet I provide. Just some important information. So how to code a graph as a matrix. So the obvious way is to use an adjacency matrix in which you have each row or column that correspond to nodes. So for instance, this graph here is represented here as an adjacency matrix. So you have so this corresponds to node 1, node 2, node 3, node 4, node 5, and node 6. And if you have a connection between 1 and 2, 1 and 5, and 1 and 6, so you put a 1 corresponding to the column 1 and 2, 1 and 5, and 1 and 6. Okay, so this graph is encoded here. What is interesting when you have this matrix representation is that you can compute some things easily by just doing operation on this matrix. So for instance, if I take the square of the matrix here, it tells you, so multiplying the matrix by itself, it tells you the number of walks of a given length that exist between any pair of nodes. Okay, so for instance, this tells you that between 1 and 1, there are 3 paths of length 2. Basically, it's going to another node and coming back. Okay, but it tells you also that to go from 1 to 2, there are two paths of two walk of length 2. So from 1 to 2 of length 2, you can use 1, 5, 2 or 1, 6, 2. Okay, so just multiplying the matrix by itself, you have this information of the number of walk of a given length between 2 nodes. And this can tell you something about, for instance, maybe 2 nodes are not directly reachable. There is no link directly between them. But if they have a strong value in this matrix here, it means that nevertheless it's quite easy for them to interact because they have many different ways to go between, or to move from one to the other by path of length 2, by walk of length 2. Well, if you multiply also a matrix by a column vector, this represents a kind of a diffusion phenomenon. So again, we will go back to that when we have a class on spreading on networks, but and also in machine learning. But basically, if you take a matrix, if you take a vector, you multiply them, and then you get each like the values in the vector represent to some values that you put on the nodes, and each node is kind of sending its value to its neighbors. That's the interpretation. And then you can work on the Laplacian. So the Laplacian of a graph is defined as follows. You have your adjacency matrix here. You build what you call a degree matrix. So in the degree matrix, you have on the diagonal the degree of the nodes, very simply. So the node number 1 has a degree of 3, node number 2 has a degree of 5, and so on and so forth. And then you take the degree matrix and you subtract the adjacency matrix, and you get your Laplacian. So basically, the Laplacian is used to represent the difference between, to analyze the difference between one node and its neighbors. That's basically the idea of the Laplacian. So to analyze this kind of properties in the network. Are nodes similar to their neighbors or different on them? So when we analyze the Laplacian, we analyze this kind of properties. And then spectral graph theory is a whole field with many research on it. So I won't go into the details here, but for instance, you can analyze the eigenvalues of your here it's the eigenvalues of the adjacency matrix, and you can have interesting properties of the number of closed walk and if the graph is bipartite or not, if the graph is connected or not, things like that. And you have spectral properties of the Laplacian also, like if you analyze you know that the number of zero eigenvalues of the Laplacian, for instance, give you the number of connected components. So by computing these eigenvalues, you can know if your graph has several connected components or not, without having to plot it or to compute it using an algorithm. You just have to compute your eigenvalues. So for those who are not familiar with these notions, it's not a problem. We won't go into mandatory details on that in the class. And then the final one is the random walk matrix. So in the random walk matrix, you are describing if you move randomly on your network. So it means you start from a node, and then you pick a neighbor, and you pick again a neighbor, and so on and so forth. And how do you move on that matrix? And basically, it just consists in dividing the fact that you have an edge or not by the degrees of the nodes to get the probability to reach that node according to a random matrix. And this we will go into more detail on it when we talk about, for instance, the PageRank algorithm in the next class. So just to give you the. Okay, I will finish with an example of a graph analysis. So as I said, what you will have to do for the project is to take a real graph and to analyze it. So in this first class, I have to kind of give you an overview of what you can do as description of the graph itself without going into the details of the nodes and other complex aspects, just a general notion. So here I will take an analysis of the graph of the Facebook friendship that was done on Facebook on 2011 and see what they have done and what kind of interesting observation we can make. So first they start by counting the number of users. So at that point it was only 700 million users active in the last 28 days. So now it's more like 2 billion, I think. Well, it depends how you count and if you trust their numbers or not. But at that point, it was something like that. 68 billion edges, an average degree on 190. So here the nodes are accounts, active accounts, and edges correspond to friendship. So this tells you that in average on Facebook, an average person has 190 friends. The median degree is 99. So this tells you that the average, well, if you take one person at random, you see that it's much smaller than the average degree because you have a broad degree distribution. But we will see that just later. And you have a strongest connected component, which contains 99.91% of all the accounts. It means that nearly everyone belongs to a single large network in which you can reach all the other nodes. That corresponds to what I explained before about this shortest path. So there is still like 0.09% of nodes that are disconnected, but probably most of them, I think, belong to well, they are singletons or things like that. There are some small connected components, and I don't know, they don't really say what they correspond to. So then you can plot your degree distribution. So you have the degree on the x-axis, and on the y-axis, you have the fraction of the nodes that are of this degree. And what you see is that it's not exactly neither a power law distribution nor a normal distribution. But looking at it, first it tells you something. It tells you that here you have a problem at 5,000. There is something weird happening. That you have some very quick shrink in the value. Why? Because at that time Facebook has a limit of the number of friends. So they were at that time you had only bipartite connection. I mean reciprocal connection. So there was no famous account that you could follow without being followed back. So there was this limit of 5,000, and this prevents from having this power law phenomenon I was explaining before. You cannot have, like on Twitter, you have people who are followed by millions of other accounts, but in this reciprocal friendship, it's not possible to have that. And so you cannot have a real power law with a very large values here. So it stopped at 5,000. And apart from that, you see that, yeah, you have still something which is clearly not a normal distribution because so you see that there are still many values around 5 and many values around 50 and many values still around 500. So you cannot say there is a typical user, this typical user has 100 friends, and basically everyone has 100, 150 or something like that. So no, you have really different types of users with many different number of connections. Then you can study, for instance, the clustering coefficient, but studying it by degree. So you don't just compute one single value, but you're interested in 4 people with a given degree, because we said that there are very different cases. There are really people with very different degrees. So you want to check if people with a given degree, what is the average clustering coefficient? What is this value? And so you see that it's kind of decreasing with the degree. So for people that have very few connections, they have a large clustering coefficient. So probably it's a group of friends. They all know each other basically. While people who are very popular, that have around 1,000 friends, probably they make friends with a little bit everyone. So if you make friends with everyone, you will have one person from one group, another person from another group, and so on and so forth. So obviously your clustering coefficient, the number of triangles in your neighborhood, is decreasing. So this tells you something about also how the network is organized. So this means that in average, 14% of users with a common friends are friends. And this is much larger than in a random network. Yeah. And then you can look a little bit at the properties of the node and how the network is organized relatively to this property. So here, for instance, is the notion of looking at the age of people. So you have on the x-axis what is the age of users, and on the y-axis you have the fraction of users who are friends with a person of a given age. So to understand it, let's look, for instance, at the blue line. So blue line corresponds to people who are 30 years old. And for those people who are 30 years old, they plot the distribution of the age of their friends, of the people who they are connected to on Facebook. And what you see is that there is a sharp peak around approximately 30. So this tells you that people who are around 30 years old, they tend to be strongly connected to other people with the same age. And it's a very clear pattern. It's true also it's even stronger for 20 years old. We see that it kind of decreased by age. And the only maybe ones that do not follow this rule are people who are about 60 years old. So why? Well, maybe because people who are 60 years old are on Facebook mostly to get in touch, keep contact with their children or grandchildren. So maybe they connect a lot with younger people than with people of their own age. Although there is still this peak around this age. So this is called homophily. We will talk again about that later. But yeah, it's this notion that people tend to connect to people that are similar to them in networks. Not always, but it's very common. So we can do the same observation with the degree of the nodes. That's on the right here. So same idea, you take people that have a given degree. So the blue line here corresponds to people having a degree of about 50, so about 50 friends. And you count the number of friends, the degree of their neighbors in the Facebook network. And again, what you observe is that people who have approximately 50 contacts, well, they are connected with people having approximately 50 contacts too. So there is this kind of homophily also in terms of degree that we call assortativity. And something interesting too is this observation that if you compare the degree, if you plot the degree of node relatively to the neighbor's average degree, you observe that it's not that is a little bit counterintuitive. Is that if you have 200 friends, so if you have 100 friends, you see that in average, your friends, they have 400, a degree of 400. So let's say that you have 100, you have a degree of 100, then your friends have 400. If you have a degree of 200, your friends have a degree also of much more than you. Even if you have like 400 contacts, then again, your friends in average, they have much more friends than you. So this is called the friend paradox. And it emerged naturally from from random network with heterogeneous degrees. But it was proposed as a possible explanation of why social network platforms can be sometimes how to say that people can be envious or jealous in social network, or maybe it's not good for your own confidence, because if you look at your friends, you see that they have more friends than you. And this is true for nearly everyone, but of course, the very popular person with a very large number of friends, and for them, they have friends with a little bit less friends than them. So this seems a little bit counterintuitive with what we have seen here. So if you have a given number of friends, you see that in average, your friends, they tend to have approximately the same number of friends than you, but still they have more friends than you. So this is just you here. This is just an artifact because this plot is in log scale. So it emerged from the property that there are some very famous people. So if you take, if you look at the average degree of your friends, in your friends, among your friends, there is a high chance that there are some people who have a very large degree. So they have a very large degree, so they have a large chance to be connected to other people, because the definition of degree is that they are connected to many people. So they are connected to many people, and they have a large degree because of that. So this will increase the degree of the neighbors of all the other nodes in the network. So this naturally emerged from And finally, this is another observation they have made. They have plotted here the matrix of the strength of the connection between countries. So each line or column corresponds to one country. So you have Italy here, you have I don't know, Portugal, France, Belgium, and so on. And they just count how many friendships you have between people from one country and people from another country. And the more green the color, the stronger the link, and the more blue, the weaker the link. And clearly you observe here that there is a structure. So probably you can guess that you will find Europe maybe around there. So I don't remember very well. I don't see very well the structure here, but you can look at the details. I think there is like Asia here. There is maybe South America around there. And then you see, so these are groups clearly identified, but you also see some exceptions with some countries which are strongly related to other countries in other groups. So I think there is Spain, for instance, I think, which is here. So part of the, and you see that it's part of the European group, but it's also part strongly connected to the Latin American group because of language and history, of course, for instance. So this tells you a lot about how the global pattern of social relation in the world is organized, for instance. But still 84% of all ages are within countries. So obviously various countries stay important. And I think that's all for today. And it's about time, so that's good. I don't know if you have a question right now. So next class is on Thursday, and it's not in the same room, you know, it's in the C room, which is on the ground floor. That's all for me. So if you have questions, you can ask them. Otherwise, you can see you next few classes.
Thank you.